Good morning, everyone. My name is Sarthak Kapoor. I am a computer science graduate student here at University of Florida. I am here in front of you presenting my project for the subject Pattern Recognition and Intelligence System with the title of Implementation of Deep Learning using Keras. Deep Learning is a deep learning technique that makes use of conditional generative adversarial network, or else called CGAN, for deep learning images. The authors of the initial paper that proposed DeepLearn have already implemented the program using PyTorch, and the performance, as per their claim, is 5 times better than that of the closest competitor. This project is an attempt to implement the same method using Keras with a TensorFlow backend. I'm going to start by briefly discussing the problem of blurring. Image deep learning is one of the image enhancement techniques used as a pre-processing task for other major problems like object detection, feature extraction, traffic analysis, etc. Deep blurring is a technique to reduce the blur from the blurred image. It is one of the image enhancement techniques that brings clarity to the image and is applied before processing the image for subsequent tasks. Blurry image can be caused due to various reasons. It can be reasons that you can control, like shaking of your hand or moving of the subject, and it can be other reasons such as lighting conditions or atmospheric wind that can cause a certain blur in the image. The blur model is identified as IB is equal to K into M into IS plus N. Here, IB is the blurry image, KM is the unknown blur channel, which is convoluted by, and star represents a convolution function, and the blur channel convolutes the sharp image, and N represents the noise. Now I'm going to briefly discuss what GANs are. As taught in class, the main concept of GAN is that two models compete against each other, and the generator tries to fool the discriminator. These two models try to converge independently and simultaneously. The training of these models are challenging because one model must be kept frozen while the other trains. GANs are mainly used for image-to-image mapping problems where the general methods fail. Now, deep learning GAN, as I discussed, is a deep learning technique that is used for deep learning and uses conditional GAN and a loss function. The original paper that the authors have presented has already implemented the deep learning GAN implementation in PyTorch using a VGG19 feature map for perceptual loss. This implementation is based on Keras using a TensorFlow backend along with VGG16 for perceptual loss. The training data that I have chosen is the same as the original authors have chosen. It is the GoPro large data set, and the link has been provided in the project report. It consists of approximately 2000 train images and more than 1100 test images, and the data is by default split. While working on this data, I realized that due to the large size of data, the training and subsequent loading was taking too much time. After digging a bit, I realized that if I pre-process the images and store them as an numpy file with the .npy extension, the dataset gets reduced almost 8 times. This also helped because while looping during the training, the images in the MPY format are loaded faster. The end result of pre-processing is that all the files that we get are of the dimension 256 by 256 by 3 numpy arrays, and they are arranged suitably in folders that will be used for training. This is the only pre-processing that has been done on this data in this project. I'm not going to talk too much into the detail of the architecture of deep blue GAN because this project is mainly focused on implementing the same architecture using Keras. So the architecture is same except one exception, that in this implementation we are using VGG16 for perceptual loss instead of VGG19 as per the original implementation. Now comes the training specifics, the training parameters and the choices. The model is trained for 200 epochs as compared to the original implementation, which was trained for 300 epochs. This was done due to time, mainly due to time constraint and also due to limited computing power. As I talked earlier, the perceptual loss is implemented using VGG16 as compared to VGG19. I have referred to the implementation of a Russian data scientist Rafael Mutek, who has implemented the same deep blue GAN implementation in Keras, and his repository is available on GitHub. Though I have referred to his implementation, this project in no way is a replication of his approach. Now I come to the evaluation of a model. As I talked, the model was trained for only 200 epochs. This is almost two-thirds of the total of the original implementation, because the original implementation was done by training the model for 300 epochs. I stopped the training after 200 because of one, time constraint, and second, to prevent overfitting. The dataset is not very diverse, so I thought it might be useful that I stop the training at 200 epoch. In this figure, you can see that the perceptual loss versus epoch graph is drawn. You can see that the perceptual loss keep on decreasing exponentially during the first 50 epochs and then takes on a linear approach until it reaches close to 200 epochs. This is a good indication that the model is converging. The next evaluation is done based on the PSNR, which is the peak signal to noise ratio versus the epochs. As you can see, the peak signal to noise ratio, when it starts off low and keeps on gradually increasing until it reaches a peak around 24.324. This is the highest PSNR ratio that I have been able to attain during the training. The final quantitative analysis is compared to the deep blue GAN original paper implementation, and as you can see, the implementation is, although trained only for 200 epochs, but the results are comparable to the results for the PSNR and the SSIM metric is comparable to the original deep blue GAN implementation. Now here are the few of the screenshots that I collected from the database, and the images are after training. The first set is the blurry image that was given as an input to the model. The predicted image is the output from the model, and the target is the sharp image that the model, the predicted image is aiming as close. The predicted image is aiming to be as close as to target as possible. As you can see, the images are visually clear. There is no additional blur added, no contrast has been added, and it appears that the context is more clear and there is no loss. Here are some few other examples. The examples are continuing. Here I present you the timeline and the work summary that was done in order to achieve this product. It started with pre-processing the data, the figuring out of how to handle large sizes of data, and then coming out of the way to convert it into .np5 files. The major portion of the implementation was GAN implementation, So it took me at least 1 week to code, bug fix, and then tune the GANs. Day 9 and 10 was dedicated to training the data. I started with local training locally, but it was taking too much time. So I shifted my code to Google Colab and mounted my Google Drive onto it, to which I had uploaded the dataset. Day 11 and 12 was the test coding for testing and testing parameters such as PSNR and SSIM. Day 13 and 14 was dedicated for the finalization of the code to write the major report and followed by preparing the presentation. In this project, we have successfully implemented deblur GAN with perceptual loss. This was a good challenge to take on as GANs have been taught to us in this class, but the practical implementation was a bit of a challenge. I had to learn how to train each model by freezing weights of the other model, in this case generator or a discriminator, and how the two models converge. The metrics obtained for PSNR and SIM were comparable to the original implementation, so this proved that this is a successful implementation of DeepLearn. And to end, the model successfully converged, which was, as I talked, the major challenge, because to convert, this was my first time writing code for uh, GANs, and it was a challenge. I end this presentation with a thank you note, and I'll be moving forward to show you the demo of the code. I've opened my Google Colab sheet notebook on which I finally shifted my code to because the local training was taking some time. I mounted my drive and now I'll be running the code in front of you as part of the demo. All of the test files are in my Google Drive, and soon a notification would come that my drive has been mounted. For this demo purpose, I have loaded the weights that I have previously saved. I'll show you in the code right now. These weight files are in my Google Drive. I knew that the original training of the model would take some time, so it can't be fitted into a 10-minute video. So I saved the weights for 195 till 195 epoch, and the model is getting trained right in front of you for the last 5 epochs. Here you can see I've received the output for the PSNR iteration by iteration, and the final PSNR ratio has come out to be 24.32, which I have specified in the PDF and the presentation. It's still calculating the similarity index, and it should be done in a couple of seconds. Yes, so the value comes out to be close to 0.75 as mentioned in the presentation and the report. Thank you.